So the friends, the topic is naming of the mononuclear compounds. So what are the rules for the naming the mononuclear compounds? And okay, so first rule is to name the cation first, center metal ion. The ligands are named in the alphabetical order. In the case of the individual ligands, we have to write mono, di or tri, but in the ligands which include the numeric prefix, we have to add bis, tris or the tetra case. And the anionic ligands will end with the O, and the neutral or cationic ligands will be the named as it is. For example, H2O aqua, NH3 amine, and carbonyl for CO, and nitrosyl for NO. Now oxidation number should be written in the Roman numerals only. That should be included in the parenthesis. And for general name, we know that the cobalt is represented as CO and platinum is represented as PT. If there is an anion, okay, then we have to add at the end. For example, this is the cobalt anion because it is negative charge complex. Okay, so we add cobalt at. These are the other examples in this complex. This is a chromium complex named as a triamine aqua chromium 3 chloride. Okay, so amine is alphabetically given the priority, and then aqua, then the chromium, that is a metal cation, okay, because of positive charge on the complex. Then oxidation number we have to calculate. These two are the neutral ligands, ammonia and water, and outside this pair there is a 3 chlorine with a -1 each charge. Okay, so when it will go in the right hand side, we can calculate the oxidation number, that is 3, and at the end chloride. This is the another example, tris ethane 1,2-diamine cobalt 3 chloride. Okay, why tris? Because numeric prefixes are given in the ligand. Okay, these are the numeric prefixes given in the ligand, that's why we used tris. Then ethane 1,2-diamine, then the cation, then its oxidation number, then the chloride. It's incomplete one, so here should be a chloride also. Okay, now this is the third example, potassium tris oxalato chromate 3 ion. Here also the numeric prefix are involved, potassium. Okay, then tris oxalato means this ligand, then the chromate because the negative charge, the anion. Okay, that's why it is given the at the end. Okay, in the case of the anion, we have to add at the end. Now what are isomers? We know that the same chemical formula with the different arrangement of atoms are called to be isomers. These are of two types, stereoisomers and structural. Stereoisomers are divided into geometrical and optical isomers, while structural are linkage, coordination, ionization and solvent. This is the geometrical isomer. Okay, so how it is a geometrical isomer? We know that here both the ammonia group are on the same side, both the chlorine group are on the same side, which is cis isomer, and here they are opposite side, so they are trans isomers. So these both are cis and trans are the geometrical isomers to each other. Okay, similarly this is octahedral structure in which all the ammonia ligands, 4 ammonia ligands are on the same side. Okay, so it is the cis, and here there are opposite side, so it is a trans, it is a geometrical isomer. Now the optical isomer should be mirror images of each other. Okay, here we know the ethylene diamine represents mirror image to each other. Okay, so it's called dextro and levo forms, we name it as it is in enantiomer. So these are the optical isomers. This is the example of the optical isomer. Now linkage isomers were given by the Jorgensen, and how it differ, we know that what are the ambident ligands. Okay, so ambident ligands are the more than one heteroatom donating to the metal ion. Okay, so this is the ambident ligand. This type of the linkage isomers differ in the linking the heteroatom to the center metal ion. Here it is in the same ligand, we have nitrogen as the donor atom, and here we have the sulfur as the donor atom. These are called as the linkage isomer. They differ in property also of the showing the colors. For example, in the nitrate ion, if the O donates, then it is red in color. If the nitrogen donates, then it is the yellow in color. Okay, now coordination isomers. These are the coordination isomers. You can see that this is the complex in which ammonia is the ligand, in the similar and here we have the cyanide as the ligand, but both could be interchanged. In the case of the ammonia could be linked with the chromium also, and cyanide could be linked with the cobalt also. So these are the interchangeable ligands. So this is called the coordination isomers. Ionization isomers are in which the counter ion could be brought inside and the ligand directly attached to the center metal ion could be brought outside. So this type of isomers are called ionization isomer. Now solvate isomers or the hydrate isomers are, for example, here we have the 6 aqua molecules. So one could be brought outside and one of the chlorine could be brought inside. So these two are hydrate isomers to each other. Okay. Now what the valence bond theory tells, the valence bond theory tells that there are different coordination number, different hybridization possible, and different shapes possible. So 4 4 5 6 6. Okay, we know that a 3p orbital and 1 s orbital means 3 plus 1 4. This is the short trick. And here we have the similarly 2 plus 1 plus 1. Then we have the 5 1 plus 3 plus 1 5. And here we have the octahedral structure 2 plus 3 plus 1. Similarly 2 plus 3 plus 1. 2 plus 1 plus 3. So these are 4 coordination number. We have the tetrahedral. Then if the 4 coordination number is another possibility of dsp2 hybridization, it's also a tetrahedral, a square planar structure. Then we can have a trigonal bipyramidal, and then we can have if the 6 coordination number is there octahedral, and similarly another configuration possible in the octahedral structure is d2 sp3 and sp3 d2. So limitations of the VBT valence bond theory, where we cannot know the magnetic data of a complex. We don't know the color exhibited by the compounds. We don't know their kinetic and thermodynamic stability. No exact prediction about the tetrahedral or the square planar structures. So the structure of the 4 coordinated complexes could not be exactly known. Okay, and we don't know what are the weak and the strong ligands. So these are the limitations of the VBT. Okay, the crystal field theory tells that there is a electrostatic interaction between metal and ligand, metal ion and ligand. Okay, the ligands are point charge as anions, and ligands could be a dipoles also, like a neutral molecules. Okay, so there is a electrostatic force of attraction between a metal and a ligand. Okay, so d orbital, first of all we know that the d orbitals are 5 d orbitals. Okay, all are vacant, so there are all equal in energy. So whenever there are equal in energy, these are called to be a degenerated or the symmetrical structure. Okay, symmetry is preserved. But if the asymmetry arises, if I feel one of the electron here, then the asymmetry arises because all the 5 orbitals will not be in the equal energy. Such cases will asymmetrical arise, and the orbital will split because of the repulsion in energy. So in crystal field splitting in the octahedral complexes, where the 6 ligands are involved, where the dx square minus y square, dz square are axis, and xy, yz and zx are away from the axis. So we know that initially all the 5 orbitals are equal in energy, but due to some reason, due to ligand environment, the repulsion occurs, and this splits into 3 and 2. It means the away from the axis and the orbitals on the axis, they split. Okay, so here we know that there are 3, these are 2, so with respect to each other, and total of the 5 with respect to each other, this increase in energy or 3 by 5, and this decrease by 2 by 5. This is simple concept. And the center where the energy is preserved, okay, it is called the barycenter. Okay, we have to remember this is splitting in the octahedral complex. Now what are the factors which involved in the splitting? If the ligand is strong, then larger splitting will be there. If the ligand is providing low field, then the smaller splitting. You know that the spectrochemical series is a spectrochemical series with a stronger ligand will provide larger splitting, and lower field providing ligand will provide a smaller splitting in a complex. This is the spectrochemical series. Okay, we have to remember. Now the concept is, we know that the T2G have the 3 orbitals. And for the D1 configuration, if we put 1 electron, then it's okay. But if 2 electrons we have to put in T2G orbital, okay, we can put. If the 3 orbital we have to put in the orbital 1 2 3, okay. But the 4th electron when comes into the existence in the D4 orbital, then we get confused that electron we have to fill in the T2G only, or we have to fill in the EZ. Okay, so how we have to justify how to fill that electron, 4th electron? So if the octahedral splitting energy, okay, we know that when the orbital split, then the the energy is called crystal field stabilization energy, represented by delta O in the case of the octahedral complexes and the delta T in the case of the tetrahedral complexes. If the octahedral crystal field stabilization energy is less than the pairing energy, then what will be the configuration? The force electron will enter into the EG and it will be weak field. The ligand will form a high spin complex. But if the octahedral energy is more than the pairing energy, then the electron will not go to the EG orbital but will retain in the D4 orbital only. D4 configuration in T2G orbital only. So the configuration will be T2G4 and EG0. So there are no possibility of chances of going the force electron into the EG orbital. So it is called strong field ligand, and it forms the low spin complex. Okay, so this form the low spin complex, this form the high spin complex. Now crystal field stabilization energy in the tetrahedral complexes. Okay, so in the tetrahedral complexes there is no symmetry, so we remove the G word from here, that T2 and E, keep it as it is, and always remember there is a smaller splitting in the tetrahedral complexes compared to the octahedral complexes, and the relationship between both is differ by the 4/9, so we can calculate easily in the numericals also. So hence they form the low spin configuration. Okay, because the splitting energy is lower. So these are rarely observed, so you know that this scene is totally changed. The one orbitals on the axis come lower and orbital from the axis come higher, and this split by 3/5 and this split by 2/5. So it is called tetrahedral splitting or crystal field splitting in the tetrahedral complexes or the entities. So this is the quick revision about the coordination compounds points and theories. Few more will come in the upcoming lecture.